you are down there by 6:45. I don't promise we leave exactly at 6:45, but we should be gathered there at 6:45. And it takes like 5 or 10 minutes to get to the place, although the bus is going to face some traffic. In any case, I hope all of you can join us for the conference dinner. And okay, so now I pass on to Bruno, who is going to he's making appointments there. Okay, Bruno.
Okay, so it's my great pleasure to introduce Yuri. Actually, I met Yuri 7 years ago, something like that. Yeah, where it was at Rio 2010. Oh no, was it Rio or was it the Maresias? Yeah, another very nice event. But I'm very happy to keep this, to have started this extra Brazilian connection, because after Yuri spent 3 internships at Bloomberg in New York, and I had the pleasure to co-supervise his PhD thesis with Jean-Pierre Fouque on the functional calculus that I had started a few years before. And actually, you were very active in the field. Basically, it allows us to have non-Markov versions of many different results in quantitative finance. And here, more specifically, Yuri is going to talk about, within this framework, how to work with stochastic control and differential games.
Okay, it's here. Yeah.
Okay.
Thank you, Bruno. Thank you for the introduction. I'd like to thank Jorge for the invitation. It's very nice to talk. Yeah, it's very nice to talk here another year in a row. So the topic of this talk is how to apply functional calculus to stochastic control problems, mainly focused on the case where the path dependency, the dependence on the history, it's on the controls. Okay, so the talk is based on this paper. It's on archive since the beginning of this year, I think. And it goes like this. So this is the usual framework for stochastic control, okay? So we have a control diffusion. Alpha is our control. The notation here is a little different. It's already like an introduction to what we'll see with functional calculus. So the control I'm denoting by capital AT, which would be the path of the control alpha t, okay? And I'm not being precise here, but just saying that this is an admissible control. The drift and the volatility here are like good functions. G and L are the functions that define the cost functional. So this is something that depends on the control, the full path of the control. But the dynamics here, and this is what we want to generalize, depends only on alpha S, just the spot like control, let's say. Just the control at time S, okay? And we are interested in the value function here, and not, we'll see. But it's for now we are considering the infimum. You can consider the supremum, no problem. So it's the infimum over all admissible controls of the cost functional here. So you have a terminal cost and a running cost. And here as well we have alpha S, so just the spot control. Okay, this is the usual stuff. And we all know that this, like under some mild smoothness assumptions, we get that V, this value function here, satisfies the HJB equation given here. Where the infimum here, now we move from an infimum over all processes to an infimum over the values, the possibilities of the control, the value alpha here. Maybe I should have used little a here. But you see that depends only on so we have dependence here only on the volatility, the drift, and the loss function here, the running cost, okay? notation multidimensional, but the main point here is that we can like take this infimum is much easier than taking this infimum here, usually, and just substitute the values of the derivatives and try to solve this nonlinear equation, okay? And our goal now is to generalize this to problems where the control, so this, the generalization of considering path dependency on X, this was done, it's not like something very different from the framework we are just showing here for the usual control, stochastic control problem. You just get the path-dependent derivatives. That's the good thing about the functionator calculus, that for most generalizations, it's a good and a bad thing. It's bad for publications, but good like for the theory. Because all the generalizations, the simple ones, let's say, they look just like the same thing as in the usual setting. You just change the derivative. So this is like some proof, let's say, that the notation and the ideas are good, that these generalizations are easy to understand and to work out. But here we are doing something quite different. We are considering, and that's the point, path dependency in the control. So you act now, you know everything up to now, and then but the control you chose at time t minus tau, for example, in this example here, acts in your diffusion at time t as well. So if you look at here, we are using the function notation. So capital X is the path. So I'm allowing for dependency on the state space, the path of the state space. It's OK. But the main thing here is this AS, capital AS. So this is the path of the control up to time S. OK? And then the idea, like, and I suggest you to have this in mind, this kind of examples, came from a visit. I spent some months in Santa Barbara, maybe 2 years ago. And Jean-Pierre, he was working on this systemic risk with stochastic gaming with delay. So it's a model for like borrowing and lending of banks, where alpha is how much you borrow, and then you have to pay that with maturity tau. So whatever you borrow at t minus tau, you have to pay now. So at time t, you get this type of drift. It's much more complicated than this, but this would be the simplified version of the problem. And this was like considered before in some other like type of theory, let's say, that so there are some old papers where they consider like linear quadratic stochastic control problems, and they can solve most of the stuff with forward-backward SDEs, okay? But they didn't have an HJB equation for this type of problems. And then after that, there are a couple of papers, I forgot the name of the author, but I think I'll cite at some point, that they did this, they considered this type of path dependency only with delay, but they had to smooth it out, the delay. So this spot delay, let's say this concentrated delay at t minus tau, this is a problem for their theory. They consider like a generalization that really depends on the structure of the delay, the L2 structure of the space they define, okay? And what I'm showing here, we can deal with this with no problem being alpha t minus tau, or like a continuum of like a continuum effect of delay, like an integral of from t minus tau to t of something, okay? Of alpha t times some function. And we can, I didn't consider in the paper, but it opens the door to considering any type of path dependency in the delay. Maybe any is too strong, but like for sure, like you can at least write down formally the HJB equation you should expect to get, okay? And so how does it work? So first we have to generalize whatever the things I showed before for functionals. And then you get this. So the cost functional would depend on the whole history of the state space that I'm calling here yt. And on the whole on the control you have chosen. And here you have g of xt, yt, at. What does this mean here? This is the path of x from 0t. Let me draw something here that will help you understand. So from up to time t, you have observed your yt. From, maybe this, from t to capital T, you simulate. So you have your diffusion, okay? And that is the whole path. So you get from here to here and here to here. Of course, yt could like influence the diffusion in many ways, and not just being the initial point. That's the whole thing here. So you may have diffusions depending on the history of the paths as well, and all this. And then you get similar thing for the running cost here, okay? And you define the functional, the value functional now. It depends on two things, the history of y, and then the history of the control. You can do this here. So it's interesting to consider in this problem. And then what this would be the infimum over all possible controls, where we are fixing the control from 0 to t, not including t. And then at t to forward, we choose our control, our alpha s here. Okay? So from small t, including small t, and this is really important. So we are optimizing this from small t to capital T, choosing our control, considering whatever we have observed and done. Okay? The control chosen and y that we have done here. We have, observed, and the control you have chosen as well. So this is probably the most important observation here, that zt concatenated with at, it's equal to z up to time t excluding t, okay? And then follows alpha t, which is the control we are choosing, okay? Okay, so this is the problem we want to tackle, and then I'm just going to introduce some notions. I will repeat this slide in a bit, so you don't have to remember everything here. But this creates the necessity here to consider functionals. Okay, so it depends on the function, the path of y and the path of the control, and somehow we have to take derivatives with respect to both. And taking derivative with respect to the control, it's not a good idea in general. But we'll see what will happen. So how do you do this? So this is what Bruno mentioned before, the functional calculus. He introduced this 2008, 2009 came the paper. And so the notation, I'm following his notation from his paper. So lambda t here is the CAD-like paths from 0t to 0 small t to r. All this can be generalized in many directions, okay? So the space of paths, it's the union of all these CAD-like paths. So you have paths of different domains, okay? That's why it's harder to work with this kind of objects. So the notation, as I said, uppercase letters will denote paths, okay, so functions, and lowercase letters will denote the spot value. So we use this. Small xs is xts, okay? And a functional, it's any function from lambda to r, okay? The two notions of derivatives you see, one is the time derivative, which is this quotient, the limit of this quotient here, where you're looking how the functional f varies with respect to this type of deformation of the path, where you just flat extend the last value. So you do this for small t, see how your functional changes, and see the rate of changing like this, okay, with respect to delta t. And then you have the bump, where you don't change the time domain here. Here you're changing. Here it's nice to notice that you're moving like through the spaces, let's say, through the lambda t's, okay? And here you have you are at t and you bump, just at the end, okay, by h, and you do the same comparison and collect the terms and see what's the limit, okay? So these are the correct notions. For example, it extends what we have for the usual Ito calculus, where you don't have path dependency. So you get, if f is just a function of the time and the last value, then what do you get? So here would be the function of the time and the last value. The last value is equal to the initial value, the last t value, let's say. And the time is changed to t plus delta t. When you compare the limit, you get the usual time derivative here. And for the spot here, for the bump, it's pretty similar, okay? And you can do for like various functionals here. One that I'm going to show is the running integral. So the running integral, the difference, so the running integral you can understand as the area below the curve, okay? So the running integral from 0 to the flat extended path will be the integral up to t, the smaller the time t, and then you have the area of a rectangle with basis delta t and height xt. So you get xt at the end. And then the space derivative is just 0 because it changed it only at one value, and the integral cannot see that, okay? So you see that you have many options to consider now, many options not in the financial sense, but different opportunities to consider different kind of payoffs and functionals, and it gets more interesting, okay? And like maybe no, for sure the main result of the theory is the extension of the functional Ito formula, of the Ito formula to the functional sense. And you get the functional Ito formula. Of course, here you can extend in many other directions. So you can consider jumps, you can consider like different types of, you can consider less smoothness of f, okay? And you get this. And the nice thing I was saying before, because you get the usual, it looks just like the usual Ito formula, okay? You get delta t, delta xx here, the second derivative. So it's exactly the same, but now with different, like, with the notions of derivatives that we introduced before here, okay? Okay, so this is the result we're going to use. So it's somehow it's a simple application of this result here, and we get the following. So I'm just recalling what we had before. So we have the control diffusion with path dependency. We have the cost functional with path dependency in the control here, and we get the functional value functional here depending on y and z. Okay. And remembering that this control, this joint control, this concatenation of two controls here, does not depend on zt, z at time t. Okay, so that we are choosing this value as well. We are optimizing this value as well. Okay, which is just to say that this is exactly what happens in the usual control stochastic control problem. You optimize, you choose alpha t, right? You're choosing alpha t. So we cannot say that we have chosen zt before. We have to allow this to happen, okay? So what do we know about the derivatives of v? Okay, what do we know about that? So we know the following. This delta t here, it's two paths. I haven't defined this, but you can believe me that the derivative here is the flat extension of both paths. Okay, you do both. You freeze both of the paths, the control and the y, and then compute the limit. This will be the really different aspect of the control with path dependency in the control. This will be the main creator of a different term that it was not present before. Okay, delta x. The derivative with respect to this variable here is just this, okay? This is the simple thing. And this is what I was saying, that zt doesn't, the control zt concatenated with at does not depend on on z at time t, this creates this type of equality here, that v, if you change the last value of z, which that's what this is doing, right? We are bumping the last value. This does not change the value function because we're optimizing the last value. So if you change the last value, it's just like changing, you're changing nothing to the value function. So there is no derivative with respect to the control alpha. I'm denoting like this, delta alpha alpha. So these are all zeros, and this is very similar to, so one generalization people consider, like Ramakant and Fournier, they consider this, is where they have a functional of the spot and the quadratic variation, because the quadratic variation is not the smooth functional, so that was the way they had to consider, like to include this type of functionals in their theory. After that, there is a paper by Obenhauser where he shows, he proposed a class of less smooth functionals where everything works, including, and these less smooth functionals include the stochastic integral and the quadratic variation. But with what Comte and Fournier did to consider this, they assumed this. Sometimes functionals may depend on the quadratic variation at time t, but what they had to do, it was to assume that this function did not depend on the quadratic variation at time t, because they don't know if the quadratic variation in the setting they were considering, they didn't know if it was a semi-martingale, and we would have the same problem here. We don't know if the control alpha t follows a semi-martingale. So if this was not zero, we would be in trouble here, because we will have to have I'll show in the next slide, but we'll have to have the dynamics of alpha, and we don't know that. But actually, we didn't have to ask this. It just happened that v, the derivatives with respect to the control, they are all zero, so we don't have to bother with the dynamics of alpha. Yes? Yeah.
This vertical derivative is defined on Cadillac class.
Yes.
So what is the meaning of this delta alpha v?
Yeah, so delta alpha, so what I'm just, it's no, so what I'm saying, so what happens here is the following. So I'm using y to denote the path, the frozen, the fixed path of x. And I'm using z to denote the fixed path of alpha, let's say. So the same way I'm using delta x to take derivative with respect to y, I'm using, okay, so I'm not taking derivative with respect to the process alpha, but just changing the last value of z. So the frozen control, the control you have observed. So just, this is a little, so what do you do usually in stochastic calculus? So you have capital T for the process, the value, and then you use small x for the spot value, what you have observed. Here, since we have used all the notations, I had to change letters. So this small x becomes yt, and this is the path, okay? And the same happens with alpha. So it's just a question of the way I chose to write this down.
Now my question is, what is the definition of delta alpha v?
So delta alpha v of yt_zt is the limit when h goes to 0 of v of yt zth minus v of yt zt over h. Okay?
What I mean is that it's different definition from the previous one, because the previous one was on Cadillac class. Now the ZT is...
Yeah, I'm allowing ZT to be any Cadillac path. So it's what you have done, and then you bump and see what happens. Okay? It's very, what you're saying is that alpha is usually smoother than Cadillac. Is that it?
No, could be worse.
Yeah, it could be worse. Okay. Yeah, so, okay, yeah, you're right. So maybe I didn't mention that. But I'm assuming that the space of like admissible controls is at least CAD-lag. So maybe that's not the best way to do it. But we'll see, okay? So yeah, so this type of smoothness assumption, I had to do it to consider as a functional, to consider this type of derivatives, okay? So V, the name we use is that V is predictable with respect to the control, okay? And then you have delta XV and delta XXV. They are also predictable in the control. So they satisfy this type of assumption here. And delta TV might not be predictable in the control because we move the Z up to delta T, so this may depend on ZT because we have to extend a little bit, okay? And what does it happen? So how does it change? How does this change the usual setting, the usual HJB equation that we find? So it goes like this. So this is the final cost, okay? I'm dropping some additional notation just to look simpler. So this is the final cost that you can write as VXT at the final control, chosen control. So I'm fixing AT here, okay? Yeah, so this here needs to be CAD-lag to be allowed to be inside V here, okay? And then I'm using the functional Ito formula for V here. I'm assuming that it's moved, and we can do that. So this will be V at T, ZT, which is the initial values for both here. The martingale part, okay, I'm assuming that V is smooth enough and sigma as well, integrable enough, so this is a martingale. And you get the drift here. And the drift, you have alpha U, you have this, the current control alpha U in this Hamiltonian here. So you have alpha that is just, I'm changing only the last value of the control Z. So that's how I'm using the notation. So ZT alpha minus ZT is bumping the last value by alpha minus ZT. So you remove the ZT and you're substituting the value to alpha here, okay? And then you have a dependence on alpha U here that you didn't have this in the usual stochastic control setting. So you have a dependence on the control in the time derivative. And this is the main difference we get, which gives us this following HJB equation, where I'm denoting H hat here to be the optimization in the real numbers, let's say, in a compact interval of the usual thing, which is this part, where you have dependency only in the control, only in the diffusion coefficient, the drift, and the running cost. And we have a QT here this is a functional, okay? And it depends on the whole path of Z and probably on the the cost at time t, the control at time t, okay? So this would then, Q here, it's the place where you put delta TV, okay? And then you get this type of HJB equation here, where you have Y, Z are the two paths, the usual thing. You have delta TV with the Z here. And then you have delta XV and delta XXV, which is the usual thing, the first and the second derivative and the last value. So this is a generalization of the previous HJB. It looks very different because you don't have the delta T plus something. It's all together. Okay, so it's probably very it's a tough equation to analyze within this framework of applications of the functional Ito formula to nonlinear PDEs, okay? And this just, I'm rewriting that, putting, instead of H hat, I'm writing this infimum here. So this infimum must be outside the full thing here, delta TV and the rest, okay? So this it's the real theorem we have. So if V is C12, so we assume that the value function is smooth, you get a verification theorem. So if you have a smooth solution of the HJB PPDE here, Under mild integrability condition, the value function is always smaller. And if you have an optimal control, AT, in the admissible setting here, you get the V is equal to the cost functional with this optimal control. Okay? So this is the usual verification theorem, but applying this case here. Okay? So I'll finish the presentation. So any questions up to here? Because now I'm going to apply to the thing I showed before. Okay? So we get the drift is just the control time t minus the control time t minus tau. Okay? The volatility is sigma. The running cost is quadratic in the control and quadratic in y. And the final cost is quadratic as well. So it's a linear quadratic problem we have. And we consider the following zats that we expect that the value function will be also quadratic in y and z as a path. Okay? So we get this y squared, y times this integral, and the double integral, and some just time function, the constant we have here. Okay? And then we can compute so now we have to put this within, inside this infimum here. We have to compute the infimum. So you have to take the time derivative, see what depends on the last value alpha. You have to consider the volatility. This will not depend on the last value alpha. This here will depend on the last value, will be alpha minus zt minus tau. And this here will not depend. Yeah, will not depend on the last value. So if you compute the time derivative for these ansatz here and put on the equation and look, whatever depends on alpha, you get this. So you get this part plus the usual part here. And then you take derivative and put equals to 0, and you find that the infimum is attained at this value. So what I was mentioning before, that we have this other theory they consider like a different approach. This part of so they get the same thing, the optimal control is equal, of course, but they get this part not from a time derivative, but they get from a different derivative that bumps only the delay part. So they create this infinite dimensional space, and they consider all this type of derivatives there, and then they get this from a different derivative. But we see that this is fundamentally like a time derivative. Okay, it is a time derivative in essence. You can try to change this a little bit. You see that, just to be honest here, it's not very nice in some sense, because to compute this, to have this PPDE here, somehow you have to guess V and see if it works. But in practice, that's mostly what you do. You guess something and you put this here, and then you see what happens. Okay? So that's what they did. For the paper by Jean-Pierre and his co-authors and the papers they based their analysis on, they all assumed these ansatz, and they took derivatives and saw what happened. So we did this, and we get that, and then you put this back in the equation, and you get this. So this is just putting zeros at the last value. So the last value of the control here is 0. Here it doesn't matter because it doesn't depend on the last value of the control. And you get an alpha square hat. You can do this. You can take the alpha square hat, get the usual first order derivative square. Everything that usually appears will appear here. And you get exactly the same equation these other people found. And you get the same system of PDEs. If you set this to 0, you match coefficients, and you get this PPD, this bunch of PDEs here. You can solve numerically. It's fine, no problems. Okay? So just to conclude, so we have extended the usual stochastic control problem to path dependency in the control. Okay? And we have analyzed only the delay control problem here in the paper as well, but he opens the research problems, now they can consider this different type of path dependency in the control. And I didn't show the stochastic gains, it's in the paper, but you can do like at least closed loop Nash equilibrium within this framework, okay? So thank you very much.